learnt that the entire positive charge and most of the mass of an atom is concentrated at its center, which is referred to as the nucleus. Generally, mass of a substance is measured in kilogram, but in the atomic sense, this is a very, very big unit. Hence, atomic mass and also the mass of its constituents is measured in atomic mass unit denoted by AMU or U. Atomic mass unit U is defined as 1/12 of the mass of a carbon-12 atom. Mass of a carbon-12 atom is 1.992647 into 10 power minus 26 kilogram. Thus, one atomic mass unit is approximately equal to 1.66 into 10 power minus 27 kilogram. A mass spectrometer is used to measure atomic mass accurately. This involves considering the various isotopes of an element. Let us first learn about isotopes of an element. Elements available naturally may be composed of atoms having the same number of protons but a different number of neutrons. Thus, we have atoms of the same element having different mass numbers or atomic masses. Such atoms are referred to as isotopes of the element. The isotopes of a given element occupy the same place in the periodic table as they all have the same atomic number. However, they may differ in their nuclear properties. Among the various isotopes of a given element, some may be more abundant than others. The percentage of a particular isotope of an element found in the nature is known as its relative abundance. Practically, every element consists of a mixture of isotopes. For example, the lightest element, hydrogen, has 3 isotopes, namely protium or hydrogen, deuterium and tritium, having masses 1.0078 AMU, 2.0141 AMU and 3.0160 AMU respectively. Of these, the lightest isotope has a relative abundance of 99.985% and its nucleus is called the proton. The average mass of an atom or atomic mass is obtained by the weighted average of the masses of its different isotopes. For example, the atomic mass of hydrogen is the weighted average of the masses of protium and deuterium, the 2 natural isotopes of hydrogen. The relative abundance of protium is 99.985% and that of deuterium is 0.015% and their atomic weights are 1.0078 AMU and 2.0141 AMU respectively. And knowing these values, we calculate the atomic mass of hydrogen and it is found to be equal to 1.00783 AMU. The nucleus is positively charged because of the constituent protons. A proton carries 1 unit of fundamental charge, E, and is stable. The total charge on the electrons in an atom having an atomic number Z will be equal to minus Ze, since each electron carries a charge minus E. As every atom is on the whole electrically neutral, it should have a Ze positive charge. This makes it clear that the nucleus has Z protons. If we assume that the electrons and protons are the only constituents of the nucleus, then the atomic mass should be equal to the sum of the masses of protons and the electrons of the atom. For example, hydrogen has 3 isotopes whose atomic masses are 1.0078 AMU, 2.0141 AMU, and 3.0160 AMU atomic mass units, respectively. If we look at hydrogen, its atomic mass is exactly equal to the sum of the masses of the proton and the electron in it. Hence, the difference between the atomic mass and sum of the masses of the protons and the electrons is equal to 0. But, in the case of deuterium and tritium, this difference is not equal to 0. This indicates that apart from protons and electrons, there are other particles present in the atom. Now let us look at the experiment conducted by Chadwick that led to the discovery of the unknown particles that were existing in the nucleus along with the proton. Chadwick's experimental setup consisted of a polonium source, which emitted alpha particles towards a beryllium target. The particles emitted from beryllium were found to have carbon nuclei along with some neutral particles. The neutrality of these emitted particles was tested by passing them through the region between the charged plates of a capacitor, where they were found to be neutral. These emitted neutral particles are made to fall on paraffin wax. The particles resulting from paraffin wax are hydrogen nuclei, which are nothing but protons. These protons are made to enter a cloud chamber where they ionize the gas present, resulting in an ionization current that can be detected by a galvanometer when the current flows in the external circuit. Initially, it was assumed that the neutral particles emitted were photons. But the neutral particles were able to knock off protons from the paraffin wax. Studies showed that to knock off a photon should possess huge energy. But the neutral particles observed in the experiment possessed much lesser energies. Yet, they were able to knock off the protons from the paraffin wax. Therefore, Chadwick assumed that these neutral particles were of the same mass as that of the protons. Calculations done on the basis of this assumption by applying the law of conservation of energy and momentum showed this assumption was in excellent agreement with the results obtained experimentally. The nuclear reaction occurring in Chadwick's experiment can be summarized as 2He4 plus 4Be9 gives 6C12 plus 0N1. Here, 0N1 represents the neutron. Thus, a neutron is a neutral particle having a mass nearly equal to that of a proton, which is equal to 1.00866 AMU or 1.6749 into 10 power minus 27 kilogram. A free neutron is unstable, just like a proton, and has a mean life of about 1000 seconds. A free neutron decays into a proton, electron, and an antineutrino. Therefore, the nucleus consists of positively charged protons and neutral neutrons. Neutrons and protons together are called nucleons. The total number of nucleons in a nucleus is called the atomic mass number and is denoted by A. The total number of protons in a nucleus is called the atomic number and is denoted by Z. The total number of neutrons in a nucleus is called the neutron number and is denoted by N. In the notation for the nuclear species or nuclides, X is the chemical symbol of the element. A is its atomic mass and Z is its atomic number. For example, in the nucleus of carbon-14, the notation for the nuclide conveys the information that this carbon nuclide contains 14 nucleons, 6 protons and 14 minus 6 equals 8 neutrons. Isotopes are nuclides of the same element but with different mass numbers. For example, carbon-12, carbon-14 are said to be isotopes of the carbon nucleus. Similarly, H1, H2 and H3 are said to be the isotopes of the hydrogen nuclide. H2 is referred to as deuterium and H3 is referred to as tritium. The deuterium nucleus has 1 proton and 1 neutron, whereas the tritium nucleus has 1 proton and 2 neutrons respectively. However, all isotopes of an element have the same number of protons and electrons. Since the chemical properties of an element depend upon the electronic structure, isotopes have identical chemical properties. Other than isotopes, there are isobars and isotones also. Isobars are nuclides of different elements having the same number of nucleons or the same atomic mass number, A. For example, tritium and helium-3 are different elements with the same mass number and hence can be termed as isobars. Isotones are nuclides of different elements having equal number of neutrons but different atomic numbers, Z. For example, silicon-30 and phosphorus-31 are example for isotones since both these nuclides contain 16 neutrons, as is evident from their notation. Until now, we have discussed about the constituents of the nucleus and different types of nuclides. Let us now look at the size of a nucleus. In an experiment suggested by Rutherford to his students, a gold foil was bombarded with alpha particles of kinetic energy 5.5 MeV. It was observed that the distance of closest approach of the alpha particle to the gold foil was 4 × 10⁻⁻15 meters. The scattering in Rutherford's experiment was assumed to be purely due to Coulomb's repulsion. As the positive charge of the atom is confined to the nucleus, the size of the nucleus had to be less than 4.0 × 10⁻⁻14 meter. Rutherford's calculations were based purely